Okay, I want to discuss one question with you guys here. This is about diffusion, temperature, time, heat treatment specification. So this problem actually involved the non-steady state diffusion, which in this case automatically you know that you have to use the second Fick's law. Still remember the second Fick's law? This is the formula that you will be using to solve the question, okay? And you're also going to use this equation in the problem, which is the temperature dependence of the diffusion coefficient, in which you probably need to calculate your D. Alright, so let's just go through this question. The wear resistance of a steel gear is to be improved by hardening its surface. This is to be accomplished by increasing the carbon content within an outer surface layer. So this is like the surface of the gear, of the steel, okay? As a result of carbon diffusion into the steel. So you're going to have your carbon to diffuse into this steel. The carbon is to be supplied from an external carbon rich. So this is carbon rich area at an elevated and constant temperature. So the initial carbon content of the steel is 0.2 weight%. So the initial part of the carbon content here is C0 is 0.2 weight% at the steel. Okay, the carbon content of the steel, whereas the surface concentration, and at the surface concentration here on the surface itself is 1 weight%. For this treatment to be effective, a carbon content of 0.6 weight% must be established at a position 0.75 below the surface. So let me just draw this a little bit larger. So this is your steel, okay? And this is your surface, in which the concentration of the carbon here is 1 weight%, and the CS is 1 weight% of carbon. And C0, carbon content of the steel, the initial carbon content in this steel is initially, alright? So we call it as C0, 0.2 weight%. For this treatment to be effective, a carbon content of 0.6 weight% must be established. So according to this problem, the atom actually need to diffuse from this high concentration of carbon, alright, into this steel until it travels as much as 0.75 millimeter below this surface, in which the carbon content here would be, the CX, would be 0.6 weight%. And then specify an appropriate heat treatment in terms of temperature and time for temperatures between 900 and 1050. So it asks you to actually come up or maybe propose a set of temperature and time. So this is your temperature and this is your time. At temperature 900 and at temperature 1050 degrees Celsius, what would probably be the time at each of these temperature? Meaning when the diffusion process is happening at 900, what is the time taken for the atom to diffuse up to 0.75 millimeter down the surface of the steel to actually achieve 0.6 weight% of carbon content? And then another one is 1050 degrees Celsius. So what are the times? So it's very important for you to really understand what the question wants. Okay, then only you can work out the solution. So first and foremost, of course, I already mentioned that this is a non-steady state. So you have to use the second Fick's law, in which you need to identify all these items, which I already stated here. Okay, and then moving on. So this is the fixed second law equation. You just plug in all the values of Cx, C0, and Cs into this equation, equals to 1 minus error function of this. So still remember this thing? The one in the bracket here is the z term. Okay? So this is something like ERFZ. So solving this part and this, you will get 0.5. Okay? Equals to the error function of this term. If you still remember here, so the ERFZ, which is 0.5, is around this one. It's around this one. Okay, so 0.5 is located somewhere here. So you need to do interpolation for you to be able to work out what is the value of Z in this case. So you want to know the value of Z here. For error function Z equals to 0.5. So please interpolate this. You will get, this is Z, okay, alright, this is Z. Z equals to 0.4747. Okay, and then you can work out what is dt, because x, you know, is 0.75, in which you can convert it into meter. So just plug in the values inside. So this is x in meter, and this is 2, and this is dt. This is your unknown. Okay, equals to 0.4747. Solving this, you will get the value of your dt. Next, you use this time-dependent equation, temperature-dependent equation, okay? So you have dt equals to d naught exponential, the one in the bracket, and t. Why do you have t here? Because this one you have t. So this one you multiply with t, and the other side also you have to multiply with t, time. Because original equation, this is only d, which is this equation. See, it's only d. And if you put t here, you also have to put t at the right hand side. And then just plug in the values, d naught and qd. You can get these two values from the previous table, which is this table. So in the problem, the diffusing species is carbon, and the host metal is gamma ferrum. And the d naught is 2.3 times 10 to minus 5, and the activation energy is 148. So you can plug in the two values in this equation. This is your d naught and this is your qd in joules per mole. Alright, so watch out the units that you're using. And solving all this, you get T equals to this one in terms of temperature. So you get the relationship between time and temperature. And then it seems that, as I mentioned before, you need to specify the heat treatment in terms of temperature and time for temperatures between 900 and 1050 degrees Celsius. So it's up to you. Either you want to just provide 2, or you can provide more. So in the solution, they actually provide 4 answers here, or maybe 4 heat treatment relationship between temperature and time, which is between 900 to 1050. So they have 900, they have 950, they have 1000, they have 1050. Some of you might be asking, how can we know that we need to specify 4 answers instead of just 900 and 1050? So don't worry about this. This question probably need to improve by saying you need to work out the value of time for each temperature at 900, 950, 1000, 1050. So if you are asked to do so, to calculate 4 types of relationship between temperature and time, so they will provide you with the exact instruction, okay? But this problem is just for your understanding on how you can solve this type of question. So between the temperature of 900 to 1050, you can work out what is time by just substituting the value of temperature here. So please remember that computation of the temperature must be in Kelvin. Okay, so this in Kelvin, just substitute the values inside. So you solve this, you will get your value in your time in second, and you can convert your time to hour. So that's how it works. So this is the kind of solution that we are expecting: the temperature and the corresponding time for each of the temperature. So just substitute je lah. 950 into this equation, you will get your time. 1000 into this temperature time equation, you will get your time, and then you convert to hour. So looking at this, it sort of tells us that at 900 degrees Celsius, it takes about 29.6 hours for the atom or for the carbon to diffuse into the steel to achieve that 0.6 weight percent. Is it 0.6? Yeah, 0.6 weight percent of carbon. And if we increase the temperature to 1050, you can see that the increment of the temperature will result in the decrease in the time taken for the atom to diffuse. So it means that the higher the temperature, the lower the time taken for the atom to diffuse. Okay, so if you have any question, you can always ask me. All right, and I will provide some example for you to try this kind of example. All right, thank you.